Hi, I'm Jim Harris. The title of our next talk is xNVMe and IOU ring NVMe passthrough, and what does it mean for the SPDK NVMe driver? I'm going to give a short intro and then I'm going to hand it off to Simon, who's going to go in details on what xNVMe is and how it applies to SPDK. So the agenda for the talk today, I'm going to start off with a little bit of history on SPDK, how and why did the project start, talk about the four main motivations for SPDK and how the work that we're going to talk about today with NVMe and xNVMe applies to that. And Simon's going to take over. He's going to go into details on the Linux storage abstractions, both the ones that have historically been there and the ones that have been added more recently. He's going to talk about xNVMe and how xNVMe not only leverages those abstractions, but also how that gets built into SPDK. He's going to do some performance comparisons with the different ways that SPDK can access NVMe storage, and then talk about some of the next steps for future work in this area. So to start, how and why did SPDK start? So the timeline here is 2013, almost a decade ago. It's kind of a little bit crazy to think that it's been that long since we started this project. But there were several things that all kind of came together to start this project. It started originally as just an internal Intel project, and within a couple years became open source. But some of the things that led to this project getting started was, first I remember being in a meeting with an enterprise storage company, and one of their developers said, we have all these SAS SSDs in one of these systems, but we can't get the performance out of them. There was a lot of software bottlenecks that they were seeing, and they wanted to see how they could address that. But we knew this problem was actually going to even be getting worse. NVMe had been ratified. Intel was actively working on getting NVMe SSDs out to market, but they weren't out to market yet. And so we knew this performance problem was only going to get worse. The software bottleneck was going to become more pronounced. But the NVMe OS support was ramping very quickly. Linux had drivers. I was actually working on FreeBSD at the time and wrote NVMe drivers, which meant we did have BSD licensed drivers out there for NVMe, which could be used for an open source project like SPDK. And then we were also, the group I was in at the time, the Intel Storage Group, was merged with the division that was responsible for the data plane development kit, DPDK. And they were tackling this exact same problem for network packet processing. And so there was a lot of thoughts here, what can we leverage? What are they doing for network packet processing that we could apply for storage? And so all these things came together, and this was basically how SPDK started as a project. So, really since that time, there's been, several motivations which were there, very early on in the project and still exist today. The first one is really breaking that software bottleneck for high performance storage workloads, especially for NVMe. But then building an open source community where companies can work together to innovate and collaborate in this area. But to innovate and collaborate in a couple different ways. One, developing new software, so things like the SPDK NVMe driver, which was mostly developed from scratch, but then also optimizing existing software, optimizing interfaces and libraries and protocols that the Linux kernel provides to user-space storage applications. But then with all of this, have a broad set of abstractions and implementations so that depending on the use case, you can pick ones that work for you. There's always some trade-offs with picking one or another, but this has always been important to kind of have a broad set and have it, be a set of building blocks that that can be used for different use cases. And so when we talk about NVMe, very early on, it was about the SPDK NVMe driver. That's kind of how SPDK made its name, was just being able to access and utilize NVMe drives in this very high performant and efficient way. And that hasn't changed. That's still priority number one for SPDK, is to have performant and efficient NVMe access. But to have this open source community where different projects, different developers from different companies can work together and collaborate to combine these technologies in ways that make sense. But to continue to look at how do we balance between developing new, so how do we, utilize some of these libraries that SPDK has developed and maintained, but then also how do we develop software that optimizes existing interfaces? So how do we optimize things that the Linux kernel provides, like this new IOU ring NVMe pass-through that Simon's going to talk about. And finally, just having this broad set of abstractions and implementations. So moving forward, we're still going to have the SPDK NVMe driver. There's a lot of use cases where that's going to make a lot of sense. But there's going to be other cases that Simon's going to talk about where utilizing the Linux kernel interfaces is also a very attractive solution. And so Simon's going to talk about how xNVMe enables that, what some of those new interfaces are, and show you some good performance data that bears that out. So with that, Simon, take it away.
Thanks, Jim. So for this part of the presentation, we'll be taking a closer look at operating system managed storage abstractions and when and how they fail, and expanding on that, what the alternative is and when and how that fails. With that in place, then we'll go over a solution promising to fix these challenges, consisting of generic namespaces and IOU ring command, and specifically how that is integrated into SPDK through xNVMe and the bdev xNVMe module. We'll then go through a performance comparison showing you how the solutions stack up to each other and a view on where the solutions are today. And by then we'll cover next steps showing you where this is going. Great, so let's get started on the why part. And to do that, let's initially say, what is it that we're trying to do where we're saying the abstractions are failing? Well, we coined the term of speaking NVMe, which is meant to refer to doing things such as doing reads and writes using extended LBA formats, like inlining your extra metadata inside of the command. It could be extensions to your NVM commands, such as doing annotations with directives, writing zeros, or doing device-side copy. And areas such as lifting responsibilities from the device up into the host, such that what you do with CNS, where the application, or at least the host, needs to do device-side management of the media and knowing what the state of zones are. And there are things such as key value namespaces, where you do something that's quite semantically different, such as store and retrieve and list and delete. And new command sets are coming, doing a lot of other things. So you can say these are sort of the hardware-assisted innovations for software-defined storage. So that's sort of what we try to do when we say speaking NVMe. So in terms of storage abstractions, in Linux they're generic because that's the responsibility of a kernel to encapsulate the variety of devices. And in terms of storage, those abstractions have been the concepts of files and blocks. And they've been around for a very long time, being able to encapsulate the different kinds of storage devices in terms of files and file systems and building those on top of block devices. So why does that fail when it comes to NVMe? So just getting a device handle, and the way you do that in Linux, where everything is a file, there your NVMe controllers are represented by the device file named NVMe0 for the first controller, and the namespaces on that controller are named NVMe 0 and 1 for the first namespace on that controller. So that works well for NVM and CNS command sets as they fit into the Linux block device model and the extension in form of the zone block device model. However, when you then plug in a device that doesn't have an NVM or CNS command set on the namespace, well, then only the controller handle appears. And that's because the block encapsulation of the generic storage abstractions of files and blocks cannot represent what a KV SSD does. And similarly for other emerging interfaces provided by NVMe, well, they don't really fit that abstractions of blocks and files. They're doing something that's very semantically different. So without a representation of these devices in the file system, then we get the first abstraction failure, which means you can't get a handle or way to open up a device such that you can try and communicate with it. The other area is in terms of device communication. So a lot have been improved here in terms of user space or user-land applications and the efficiency of talking to the kernel and through the kernel. That cost has been reduced dramatically with IOU-ring, where memory is shared in the form of rings from user land to the kernel space, and optimizations of resource registration, where that reduces lookup costs when you do commands, such as registering which buffers that you're operating on and which devices that you're operating on. By pre-registering these, it does faster lookup times for each syscall as you cross that boundary. And generally there's a cost of doing the syscall, and ways to work around that is for polling optimizations such as sqpoll. So with sqpoll you have a kernel side thread that's looking at the shared memory and seeing the commands that are coming through IOU-ring to see what the user is doing, and then you don't need even a single syscall when communicating from user to kernel space. The cost is of course that you then have a kernel side thread that needs to be listening for these things. Another way is through regular IO poll and then doing batching, where you can amortize the cost of going from user lane into kernel space by queuing up a bunch of commands and then sending only a single syscall to tell the kernel that commands are now available. However, when speaking NVMe, the things that we just mentioned, well, these things aren't available, as the representation and the commands currently available to IOU-ring are all around the generic storage abstractions of reading and writing files. So doing the things that we wanted to do when sort of speaking NVMe, well, that's not represented in the command sets for IOU-ring. So what we then have is that we fall back to the ioctl, which doesn't scale, as we try to illustrate here, where we have a flat red line on a graph with IO depth on the x-axis and IOPS on the y-axis. You can then add a thread pool, but that is very inefficient. In this example, it's using one thread to increase the queue depth, whereas IOU-ring does so efficiently on a single call. So the abstraction failure here is that we cannot use the IOU-ring facilities to natively speak NVMe. So the existing solutions, well, that's all about moving that storage abstraction out of the kernel, so lifting responsibilities, similarly to how we see that responsibilities are being lifted from the device side in terms of CNS. Well, then we can lift the encapsulation of these things from the kernel and into user space, such as the SPDK block device abstraction, and then bagging that with an efficient SPDK NVMe driver. Which brings us to the question, so when does this fail? And for that, we'll take a look at deployment environments. So a requirement to using the SPDK NVMe driver is that you need to detach the kernel's responsibility on the NVMe device in terms of running the NVMe driver, and then rebind that PCIe device to VFI PCI or UIO generic, such that the driver can be run in user space. That has its implications for hardware setups where you have multiple devices in the same IO-MMU group that prevents detachment. As that entire group needs to be detached, then all of these other non-NVMe devices also need to be detached, which might be critical for that system's function. There's also the issues with unsupported IO-MMUs or PCIe bar address space that can hinder the rebinding of the driver. There's also considerations with regards to moving stuff into the cloud, where the deployment environment might not have any NVMe drives, so what will you use then? Perhaps just some encapsulated storage device service. But more commonly, it'll be restricted in the sense that you are not allowed to do this kind of root level or system access of detaching the kernel driver. So what do? Well, then you fall back to using operating system managed devices and using the storage abstractions provided by the kernel. And as we know, that involves a lot of both performance implications and using new features from NVMe. So one part of it is that we really want to enable deployment of SPDK in environments that's otherwise unavailable, and enable deployment of SPDK in these environments with a minimal performance hit. so started to rely more on what Linux provides, such that SPDK can be run efficiently in these environments. And as such, the goals of Linux and SPDKs start to align. So what are those goals? Well, the main goal is to be able to have, or Linux to support, an open-ended representation of NVMe devices for both existing and new NVMe command sets with a fast path for communication. So that means for device handles that all devices should be brought up regardless of whether there's a Linux device model to support it, handles should be provided. And then a way to speak with it efficiently using sort of native NVMe, being able to ship commands to those devices in a user-defined fashion. And the scalability should match that of IOUring, and ideally as efficiently as the SPDK NVMe driver. This brings us to the first of three parts on how to meet these goals, and that's on generic device handles. So solution is now provided in upstream Linux, and the initial support came in Linux 5.13, and it consists of exposing the NVMe namespace as a different type of device in the file system, specifically a char device, under the naming convention of NG instead of NVMe. And with 5.13, that got introduced for NVM and CNS command sets, but now with Linux 6.0, these handles are brought up for any command set. So that means at this point in time, there's a means to get a handle and then communicate with the device using the Linux ioctl, regardless of whether there's a matching device model, and then enabling handles for both existing and future NVMe command sets. Now we just need the performance part. And that's provided by IOUring command. So IOUring command is a generic facility that allows you to attach IOUring capabilities to a command provider. It needed some changes to the general IOUring infrastructure in the form of making larger ring entries, so larger submission queue entries and larger completion queue entries, such that commands as well as their completions would have room in the ring. The really nice thing about this is the generic form of it. So it's a common command provider interface that you can attach to your driver or your file system. So similarly to where you might want to do ioctls to communicate with the subsystem, you can now do a command provider that you can access through IOUring. So specifically for our interest is then the command provider for NVMe, where you can do NVMe pass-through commands. So these you define in the same way that you do the NVMe driver ioctls, and related to this work was the need to also extend the driver ioctls with IOVIC support as a means to support the SPDK BDAV abstraction, where the IOVIC payloads are quite essential for the read and write commands. So looking at the picture here, we start to check off these requirements. We have the handles, we can speak NVMe natively, as we now have an IO path through IOUring command to talk with our devices. And for details, I would invite you to take a look at Kanchan Joshi's presentation or slides from the Linux Plumbers conference, where he goes into a bit more detail on this. So this brings us to the third part on how this new infrastructure is integrated into SPDK through xNVMe and the xNVMe BDAV module. And we'll start out with a quick introduction to xNVMe itself. Now, xNVMe is best described by what it provides. That is a core API for constructing and submitting commands with the encapsulation of buffers for command payloads. And xNVMe promotes an asynchronous programming model based on command queues with callback notification. And this is done in order to efficiently utilize hardware. Additionally, a blocking or synchronous interface is provided, and that's done such that the same command construction logic can be reused in things like command line tools. And basically also when you're just experimenting and exploring new command sets. Now this is all done in order to reduce the mental load of developers by reducing what they need to know on how to send a command down to the down to a device on a given platform, such that they can instead spend energy on what they want to do with the device. So as an example, on top of the core API, there are a bunch of commands that help us, such as for NVM doing read and write zeros, copy commands, and CNS is a good example, where you need to do, there's a bunch of management for CNS device, which first off is being sort of lifted from the SSD up to the host. And the further you can take that to the application domain, the more you can reap the benefits of using CNS devices. Now the intent is then that the user can use a single API for talking with CNS devices rather than having to learn all of the different paths they can take based on how Linux or userspace driver looks at it. For instance, you can use the block ioctls to get zone reports, or you can send an NVMe command directly or pass it through an NVMe ioctl. Here, xNVMe just provides the same API. You construct the commands and it'll send it down the path that's available to you. And currently there's a bunch of different implementations of backends, of ways of formulating your different or shipping down your commands to devices. There's all of the usual suspects of read and write, IOUring, libaio on Linux. There are thread pools for fallback when nothing is available. And most interesting, of course, is the IOUring command. So that has been part of the development of xNVMe, has been looking at these different ways of doing it and having an abstraction such that we can innovate and improve on the system interfaces without having to actually change the application. So as you see, the abstraction is sort of aligned on the same principles as the SPDK BDEV. The abstraction layer is just a bit lower, talking about abstracting the queues and callbacks rather than having a block device abstraction. So what is xNVMe used for? Well, it is used for its I/O interface independence and one of its goals of being minimal abstraction costs, such that it's something you can plug into your application where you might have been doing libaio and now you want to try IOUring. Then you can have both without having to maintain them by trying out and using xNVMe. It has a bunch of convenient command line tools, and you can do sort of rapid experimentation with it interactively through Python. And for further details, I would point you to the Systor presentation. It's on YouTube, and there's also a paper to download and the website for xNVMe. So xNVMe provides all of these different interfaces. And inside of SPDK, we added a new BDEV called the BDEV xNVMe, and it basically just calls into the xNVMe APIs, and thus provides a single BDEV implementation for all of libaio, IOUring, and the new IOUring command. By doing so, we can have one place to add these device-specific handling, such as zone management, or doing device-specific optimization, such as a device-side NVM copy. And it's integrated in the same way that other BDEVs are in sort of the layers here, similar to the NVMe, IO and IOUring, such that SPDK applications can build on top of it, and it's calling into those same interfaces. So these should be sort of well known in the SPDK community. And for further details on it, credit is due to Krishna K. Reddy, who has done most of the implementation, who's done the heavy lifting, and he has made a presentation at SDC. And I would welcome you to take a look at that. Great. So this brings us to the final section on comparison, seeing and trying to evaluate our goals of whether our IOUring command matches the efficiency of IOUring, and whether and how far or where we are with our IOUring command with regards to the SPDK NVMe driver. And we do so in a relative comparison, so don't get too hung up on the absolute numbers. We want to look at a saturated CPU and see how these different solutions perform. We'll also be taking a look at the SPDK BDEV implementations and see how they stack up. So to evaluate this, we use a system with a Core i5 in it, with SMT enabled, Turbo Boost disabled, and with 8 devices, each capable of 1 million IOPS, with a total device rootline of around 8 million IOPS. The software in use is the latest Linux version and the latest version of the tools of FIO, xNVMe, as well as SPDK, along with a small patch set introducing a flag for conserving CPU and specifically disable the conservation of CPU. To do and to utilize our uring command efficiently and to get the most out of the I/O rate, we need to tweak the kernel a bit. The kernel tweaks are provided here for the kernel config, and essentially for the driver itself, that needs to be loaded with queue polling enabled, as well as setting some flags in sysfs. So these are provided here for reference. Now we measure this using 2 synthetic benchmarks with a tool specialized for measuring our uring provided with FIO, along with the instrumentation script called one-core peak, as well as instrumenting that test script manually and using BDEV-perf. Now the logs of all of these runs are provided for you to inspect them and also try and reproduce them, which is encouraged. So let's look first here at IO uring, and what you're seeing here in these 4 columns. The first column is the default behavior when running the one-core path, which uses 1 thread per device. So that's 1 thread, 1 ring per device, where we actually flatline very early, and it seems like when measuring it that this is due to thread congestion when running. So you can tweak that by only using 2 threads, matching your SMTs, so 2 hardware threads running on the same CPU core. Here we get a peak of 4.16 million IOPS. The 2 last columns are provided for reference, such that you can see what happens if you're not enabling optimizations such as polling, as well as using command batching. And the last column here is using exclusively submission queue polling and none of the using submission queue polling. So how does this compare to our uring command, or how does our uring command compare to this? Well, our uring command actually performs better. So in the best case, we hit 4.86 million IOPS, and otherwise behave along the same trends as the regular IO uring. So in terms of evaluating the goals for Linux, we can check off these boxes. We have the handles, we can speak NVMe natively, and it scales as efficiently as IO uring. So how does this compare then to the SPDK NVMe driver? Here we use the BDEV-perf tool to do a similar experiment as done with the test IO uring program with FIO. And we'll be varying that in the same way with and without SMT, such that we can do an equivalent comparison. So on a single SMT thread is what you see on the table here, where we actually managed to reach 7.24 million IOPS. And if we enable the second thread in the second column, then we're actually saturating the drives. So why this gap? The best thing we got with our uring command was 4.86 million IOPS. And some of that goes into that this is all a generic facility, so it will in most cases always do more work and have more code behind its implementation compared to a specialized user space driver. It also needs to tap into generic kernel infrastructure and using things that haven't been optimized just yet. And we've seen, or as we saw in the numbers, our uring command actually does a bit better than just using IO on the regular interface. And that's because there were some opportunities to run less code. And there might be opportunities to reduce that even further. We also have some untapped optimizations with regards to DMA pre-mapping, such that those buffers are pre-mapped and looked up instead of having to actually be mapped once per IO. So we're not quite there on that goal of scaling as efficiently as the SPDK NVMe driver. But we've put out some plans on how we can try and improve that we'll get to in the next steps. Now comparing the BDEV implementations, well, we'll be looking at BDEV xNVMe versus uring and BDEV xNVMe versus AIO, and trying to get a sense of the overhead at QDEV1 as well as how it scales at QDEV 128. Now the reason for doing this and providing these numbers is to show you where we are at now and what we would like to improve. So first, comparing BDEV xNVMe to BDEV AIO. There things are looking pretty good. We are on the same scale, and what you see on the graphs are IO depth on the x-axis and IOPS on the y-axis. There are some things that can be improved with regards to call stack overhead that we'll be looking into. And then comparing the use of IO uring through the different BDEV interfaces. So what you see here are the purple lines are BDEV uring and the green lines are BDEV xNVMe. And this doesn't scale very well. And the differences in implementations are whether or not they're using IOPOL, which BDEV xNVMe actually does, whereas BDEV uring does not. So to get the performance improvement here, it's very important that you actually enable POL queues. And when doing so, you see a completely different picture that BDEV xNVMe is actually doing fairly well on scale here compared to the current BDEV uring implementation. So let's quickly take a look at our uring command through BDEV xNVMe. Since we don't have a baseline to compare it to, we'll be comparing it to BDEV xNVMe using our uring. And the story is the same, and it's not very interesting. What you see on the right hand side of the verses are the IO uring command usages of BDEV xNVMe. And both of these accounts is doing worse than BDEV uring using just the IO uring interface. So why is that? Well, the thing is that when this got implemented, IO uring command did not support IOPOL, which is what BDEV xNVMe is doing here with IO uring, so it had to resort to using SQPOL. And that just doesn't scale as efficiently. So we can summarize. What have you seen? You've seen that Linux 6.8 has a new efficient means for NVMe with a generic device handle regardless of what command sets are provided, as well as a generic command interface to speaking natively and efficiently with those devices. There's still a gap to the SPDK NVMe driver, but that's closing. And you've seen that this has been integrated into SPDK through the BDEV xNVMe module. And as well here, there's some work to get closer in terms of performance. So what are the next steps? Well, for our uring command, we need to do some work on the device encapsulation, matching the IO access control on file permissions and making sure that we can send commands without having capsys admin. So basically allowing an identify command when you're not root, such that we can get information such as the maximum data transfer size from the device. And then focusing on improving the efficient communication on see if we can exploit huge pages and possibly investigate some kind of DMA pre-mapping. So basically exploring how can we tweak this interface even further. For BDEV xNVMe, there's a bunch of work, and the main thing is focused on getting that performance to match what we saw in the synthetic benchmarks. So that's the main focus. Additionally, we want to expand the functionality such that enabling write zeros and flush commands and having one place in the SPDK code base for doing device-specific handling such as zone management. There is also an opportunity to explore further down the line of deploying this on Windows, where currently xNVMe has support for IOCP, and we're working on direct storage support as well. So in general, the goals for the BDEV xNVMe is to broaden that SPDK deployment while matching the interface efficiency. And next step for xNVMe, when we currently have support for things like IO uring setup with IOPOL, SQPOL, and single user, we do registration of files, but we do need some optimizations that has come along for setting up rings for co-op task run and deferred task run, and more of the resource registration. But the key thing that we need to get done is proper support for batching and leveraging the features that IOUring provides in this area. And then we have some general optimizations for SQE reuse, data structure alignment, and command construction. So what does this all mean for SPDK? Well, I think we can say that xNVMe shows the promise of encapsulating these Linux kernel NVMe interfaces for the BDEV abstraction. We have a single BDEV to handle the different libaio, IOUring, and IOUring command. We have a way in a single BDEV to handle command set specific interfaces. And that sort of enables a wider range of deployment for SPDK applications. And what we're also seeing for SPDK now is a much closer collaboration with SPDK and Linux and those interfaces, and integrating those efforts on the storage ecosystems as a whole. So with that, I just want to say thank you for listening. And in terms of collaboration, it would be great if somebody would like to try and reproduce the numbers that you've seen here, see how this behaves on your system, as well as giving input on the IOUring command optimizations. Especially also some help or input on how can we further optimize the BDEV xNVMe. And if you want to have a look at xNVMe as well, how can we tune that? Then please call out on the SPDK Slack channels where we're hanging out. We're also hanging out on the Samsung Ghost channel. That's Samsung's global open source team, which are available on Discord. So with that, thank you and see you.